Good afternoon to all. We are discussing computational complexity. So under the computational complexity, we have discussed about the decidability problem, the undecidability, the disability with reference to the context-free languages, the decidability problem with reference to the regular languages we have seen, and we have also discussed about the mapping reducibility means how the problem one problem is reduced to the another problem. And in the earlier session, we discussed about the classification of problems. That is nothing but the problem classes, P class or the P type problem and NP type problem. Now these are classified. NP type problem it is further. So basically two types of problems are there. P type or the P class and NP class or the NP type problem. Further, this NP it is categorized into NP hard problem and NP complete problem, right? So we are in this session, we are going to discuss about the NP complete problem and NP hard problem. So let us see, be focused on your screen here. Before starting the actual introduction of the NP hard and the NP complete problem, so first just go through the concept. We'll just go through the concept of non-deterministic algorithm. Now, what exactly is the meaning of non-deterministic algorithm that we'll see in these two slides. So deterministic algorithm, how the non-deterministic algorithm works. So what exactly is the difference, how their execution is different, and how they reach to a particular output is different, that we'll see with this example. Now let us see the deterministic algorithm is there. So algorithm is able, this is nothing but the execution of algorithm is able to it follow a particular path and able to reach to the accept state, is able to reach to the accept state. A fixed path is to be followed, or a fixed, one can say, algorithm is there, and the proper algorithm with the proper path it reaches to a accept state here, right? But in case of non-determinism, in case of non-determinism, we do not have a fixed path, we do not have a fixed one can say path that leads to the particular solution. So we may go to the certain path that leads to the reject state, or that becomes your reject condition, right? So in that particular path, suppose we go to this particular path and this way, and this particular way, this may go lead to the reject one. Or this particular path, if we choose a particular path like this also comes to the reject one, right? But in case of deterministic algorithm, or in case of our deterministic approach, we can say that yes, fixed approach is there, or fixed steps are there. They leads us to the accept or reject state. They leads to the accept state or the reject state. But here in case of non-determinism, you can have from current point, you can go to the multiple points from here. Suppose you are at this point, you can follow this path, first path, second path, or third path. So multiple paths are available, and it is very difficult to determine which path leads to the accept state. So somewhere here you will find that the algorithm is enters into the accept state, or this particular machine accepted the given string. Getting this point. So non-deterministic approach or the non-deterministic algorithm, they works in this particular fashion. They works in this fashion. So this is nothing but our f of n. So as we studied that the time complexity is very much high in case of our non-deterministic algorithm or non-deterministic approach. Here in case of also, in this case, if we find out the f of n value, so it is optimum as compared to your non-deterministic one, right? So see here, decision problem or deterministic problem lead to the notion of a non-deterministic algorithm. A non-deterministic algorithm is a two-stage procedure that takes as its input I. So first it takes the input I of a decision problem and does the following. It actually works in the two stages. That is, first stage is called as the non-deterministic stage, or the guessing stage. Means as no fixed solution, no fixed algorithm, or no fixed path is known, so only trial and error. So we can say that it is a simple trial and error method. It is just a trial error method. So first we go this one, we try this. No, here is a rejection state is there. So go to the another one, that is a rejection again. Then follow the next one that leads to some accept. So purely based on guessing, or purely based on your trial error, or arbitrary method is there. So we can say an arbitrary string, yes, generated that can be thought of as a candidate solution, So first stage of the non-deterministic algorithm is nothing but the guessing, means just to guess which is the correct path, but not a fixed path. We cannot say if, deterministically this is the particular fixed path. And second stage is nothing but actual verification stage in the non-deterministic algorithm. Deterministic stage, or it is also called as the verification stage. A deterministic algorithm takes both input I and input S as an input and output yes, and it will produce as output yes if S is the solution of input I. Right. So if it reaches to a proper solution from the input I, then it produces then output is equal to yes. So we say that non-deterministic algorithm solves a decision problem if and only if. So non-deterministic algorithm solves a decision problem if and only if every yes instance of the problem returns the yes on the same execution. So every yes instance must returns a yes on the same execution. Finally, non-deterministic algorithm is said to be a non-deterministic polynomial. Only non-deterministic algorithm, but we are now finding your NP. We are now defining your NP, that is non-deterministically polynomial. So non-deterministic polynomial if the efficiency of its verification stage is polynomial. If the efficiency of, so this is nothing but the correct definition of your NP, that is non-polynomial or non-deterministically polynomial algorithm. Getting this point? So its efficiency is in terms of polynomial, or it is given. So non-deterministic polynomial, if its efficiency of its verification stage, this stage, it is given in terms of polynomial, then we can say it is a NP problem. Then it is called as it is categorized as a NP, non-deterministic polynomial algorithm, or the class. So see here, class NP. Class NP is the class of decision problems that can be solved by a non-deterministic polynomial algorithm. Class NP is the class of decision problems that can be solved by a non-deterministic polynomial algorithm. Most decision problems are NP. Most decisions here, most of the decision problems are NP, that is non-polynomial or the non-deterministic polynomial time algorithm. First of all, this class includes all problems in P. This is true because if a problem is in P, that is in a polynomial time, or if it is in a P class, we can use a deterministic polynomial time algorithm that solves it in verification stage only. There is no need of any guessing stages, because NP follows the two stages. First stage is nothing but the guessing stage, means you are going to guess the path, and finally you are going to verification stage. That is nothing but this is the deterministic stage. You can say yes, verification, or it is a particular deterministic stage of a non-deterministic algorithm that simply ignores string S generated in the non-deterministic stage, Getting this point? So come it once again, just go through it once again. This is true because if problem is in a P, means if it is in a polynomial class problem or P class, we can use deterministic polynomial time algorithm that solves it in a verification stage of non-deterministic algorithm that simply ignores string S generated in its non-deterministic stage, right? Okay, so let us go to the next one, and the next point is nothing but your NP complete problem. So that's all about non-deterministic, and what exactly the relation between non-deterministic and deterministic one. So in point to be remembered here is that in case of our non-deterministic one, the two stages are followed. That is nothing but your guessing stage and then the actual verification stage. So one can say that the polynomial time or the P class is the problem is also a part of it, is a subset of your NP class. Why? Because the P class is nothing but a special case of your NP. That is nothing but where the problem only follows the verification stage and it will not go to the guessing stage. So we can say that the P. So if I draw a Venn diagram, so I can draw it is my NP problems, but P class is nothing but the part of that NP, where these P problems are only go for the verification stage and they are not go for any guessing stage. There is no guessing stage for this P class problem. Getting this point? So this is the case. Now further this NP, that is non-polynomial time or the non-deterministically polynomial time, they are categorized into NP complete problem and NP hard problem. So what exactly is the NP complete and NP hard, that we'll see one by one. So see here, informally, NP complete problem is a problem in NP, means in non-polynomial time, that is as difficult as any other problem in this class, because any other problem in NP can be reduced to it in polynomial time. Polynomial time reductions of a NP problems to NP complete problem are shown by arrow in the figure. So NP, so see here, so NP complete problems. So how the NP complete problems are defined? So it is nothing but the NP problems. So all the NP problem after reductions, they are moved towards, or they are called as a NP complete problem. So what exactly the stage? So there are so many n number of problems. So this is NP class. So many problems are there. All they are NP problems, but after reduction. So see here, NP problems to NP complete problems after reducing polynomial time reduction. So what we are going to do, what is the difference? So here, polynomial time reduction, after reducing their polynomial time, one can say that NP problem or your plain NP problem become your NP complete problem, your NP complete problem. Then what exactly the stage is to bring your NP problem? So all these are nothing but all the instances, and they all are moving toward the completeness. They are all are moving toward the completeness. And when the problem, we say that NP problem is said to be a NP complete one, when the polynomial time reduction is happening here, then we can say that yes, the problem is now become the NP complete. So let us see the procedure, how the reduction is happening here, or reduction is carried out. A decision problem D1 is said to be a polynomial reducible. So we have to find out the polynomial reducible problem, or we have to go for the polynomial reduction to a decision problem D2. So the NP problem D1 is given, and it is to be converted into the D2. And how is the D2? D2 is the polynomial reducible is the D2. So if there exists a function t, small t, that transforms the instances of D1 to instances of D2 such that transforms the instances of D1 to the instances of D2 in such a way that, getting this point. So meaning is that NP complete problem is what? NP problems are there. These NP problems, they are converted into the NP complete one after polynomial time reduction, after reduction of the polynomial time. And the method is that if the decision problem is there, suppose D1 is a NP problem, D1 is a NP problem, and this problem to be converted into the NP complete one. So how we can say that? Yes, if it is said to be polynomial reducible to decision problem D2, so it can be converted into D1 into D2, where D2 is your NP complete. So method is that this one, there must be a polynomial reduction. So how it is the polynomial reduction? So there must be instances in this problem that such that, what is the condition? So let us see the conditions. T, where T maps all yes instances of D1, the problem which is to be converted, NP problem which is to be converted into NP complete problem, to yes instance of D2, and all no instances of D1 to no instances of D2. That is the first case. And T is computable by a polynomial time algorithm. So these are the two conditions are to be fulfilled. So if I write here, D problem is there, this is my D problem, and this is to be converted into D2. This is nothing but my NP problem, and NP problem is to be converted into NP complete problem. So the condition provided that there must be some instance T, there must be some instance T that maps all yes instances, whatever may be the all yes instances of the D1 into all yes instances in the D2, all yes instances in the D2, and all no instances in D1, all no instances in the D1 that are mapped into all no instances in D2. And second case is that this T must be computable polynomial time algorithm. This is the condition. So it implies that, what implies, if a problem D1 is a polynomial reducible, if it is a polynomial reducible to some problem D2 that can be solved in a polynomial time, then problem D1 can also be solved in a polynomial time. So if D1 is a polynomial reducible to some D2, that can be solved. So D2 is a problem that can be solved by a polynomial time. Meaning is that the D1 can be also solved by a polynomial time. So a decision problem D is said to be a NP complete if and only if it belongs to class NP, the first case. And second, every problem in NP is polynomically reducible to D. It is polynomically reducible. So polynomial reducible to D. So this is the condition. So when the problem is called as a NP complete problem or non-polynomial complete problem, if and only if it belongs to NP class, okay, no problem. And this particular problem, NP problem, must be reducible, polynomially reducible to problem D. And how to reduce polynomially? So you must have a T. That T maps all yes instances of this one into the yes, all instances of D2 and all no instances into no instances of D2, and the T must be computable in polynomial time algorithm. So NP completeness requires polynomial reducibility of all problems in NP. So we require polynomial reducibility. Means reduction in the polynomial time of an algorithm. Let us go to the next point, NP complete one. NP complete problems have been found by a mathematician, name of the scientist who invented this NP complete problem, Stephen Cook and Elconid Levin in 1971. The well-known problems are the type of the problems or the problems which falls under the category of NP complete one. They are the Hamiltonian circuit, traveling salesperson problem, graph coloring problem, and partition problem. Means they are all NP complete problems. So all these problems, they are called as the NP complete problems. So remember, Hamiltonian circuit is the problem NP complete type. Then traveling salesperson problem is also a NP complete type. Graph coloring problem is also your NP complete type, and partition problem is also your NP complete type. It is known, however, that if P equal to NP, there must exist NP problems that neither are in P nor in NP complete. Showing that a decision problem is NP complete can be done in two steps. First is show that the problem in question is in NP, and the second one is that show that every problem in NP is reducible to problem in the question in the polynomial time. Means of course we have to convert that NP problem through polynomial conversion or through polynomial reduction into NP complete problem. See the figure here. Proving NP completeness by reduction. So NP completeness is to be achieved with the help of your reduction. So known NP problem. So this is, one can say that this is the known NP problem. So these are the NP problems. This is known NP problems are there, and they are now reduced. So candidate for NP complete. So they are moving towards the completeness. And how the completeness, they will achieve the completeness by reduction only, by polynomial reduction. By polynomial reduction, they move towards the completeness, right? The definition of NP completeness immediately implies that, now see the definition carefully, if there exists a deterministic polynomial time algorithm for just one NP complete problem, then every problem in NP complete problem can be solved in polynomial time by a deterministic algorithm, and hence P equal to NP, Getting this point? So just go through it once again. The definition of NP completeness, when we can say that a problem is NP completeness, or how to define the NP completeness problem. So the definition of NP completeness immediately implies that if there exists a deterministic polynomial time algorithm for just one NP complete problem, then every problem in NP complete problem can be solved in a polynomial time by a deterministic algorithm, and hence P equal to NP. Getting this point? So NP completeness is nothing but a reduction problem. Polynomial reduction we have to apply, and the NP problems they can be reduced to the NP complete problem. That is nothing but our, one can say, the summary. Next is nothing but your NP hard problems. Now the second category of the NP problems is nothing but the NP hard problem. So let us see here the decision version, the decision versions of traveling salesman problem and the Knapsack problem are NP complete one, whereas the optimization version of such difficult combinational problems fall in the class of NP hard problem. Getting this point? That means the problems that are at least as hard as NP complete problems. So there are no known polynomial time algorithm for these problems. So this point you have to remember. There are no known polynomial time algorithm available to solve such kind of problem. They are called as the NP hard problems. Meaning is that, see here, you have to remember that. So decision, the two category of the problem, that is nothing but your decision problem and optimization problem. Decision problem and optimize. Decision problem means the problem will lead to certain decision. Means after solving that particular problem, after following the number of steps, we reach to certain decision. But in case of optimization means what? Here the decision is not important, but we have to optimize the solution. We have to optimize the solution which is received from that by solving that particular problem. So the traveling salesman's problem, if we see the TSP traveling salesperson or traveling salesman problem is there. So if the decision version is there, so decision version is falls under the category of NP complete. Listen it carefully. Yeah, decision version of TSP problem or the Knapsack problem. Knapsack problem, the decision version of the Knapsack problem, they falls under the category of NP completeness. But whereas their optimization version means if we go for the optimization of traveling salesperson problem or the optimization of Knapsack problem, so definitely they falls under the category of NP hard problem. They falls under the category of NP hard problem. Getting this point? Meaning is that all optimization kind of problem, as they are, because they are as hard as to solve, as there is no one can say no known polynomial time algorithm available to solve such problems. They are fall under the category of NP hard problems. A problem A is said to be NP hard if and only if the satisfiability problem reduces to A. Hence, to show that an NP hard problem is a NP complete, we just have to determine a polynomial time non-deterministic algorithm for that particular problem. See here, there are many NP hard problems. There are many NP hard problems which are not NP complete problems. Of course, the halting problem is a NP hard problem. So already we have discussed the halting problem of Turing machine. So as no known polynomial time algorithm is available, so it falls under the category, it is called as the NP hard problem. So if we get solution by applying certain algorithm, then traveling salesperson problem is an NP complete problem. Okay, that is okay, because already we've seen that if the solution is achieved by following certain steps, then no problem, it is a complete problem or NP complete problem. But no algorithm is there, no polynomial time algorithm is there, then definitely this TSP, we call it as a NP hard problem. If we get no solution at all by applying an algorithm, then the traveling salesman problem belongs to NP hard problem. A very simple example is given. TSP, traveling salesman problem. If the solution is available, it is NP complete one. If the no solution, it is an NP hard one. Problems which are known to lie in P, means in P class, are often called the tractable one, whereas the problems which are lie outside the P, they are often termed as an intractable one. They are called as an intractable one. Thus, the question of whether P equal to NP or P equal to NP is same as that of asking whether there exists a problem in NP which are intractable or not. The relationship between P and NP, see here, now the P and NP. So this is nothing but your P and this is nothing but your NP. So this are, suppose here, there are n number of problems. So I can say that all these are problems are NP problem. Whereas these, so there are some problems, they are polynomial time problems. They are polynomial type of problem, or they can be solved by polynomial. Uh, right, they can be solved by polynomial algorithm. But here in case of NP problems, it is nothing but non-deterministically polynomial or non-polynomial time the class problems are there. So NP problems and P problems. So we don't know if P equal to NP. In 1971, Cook and Levin proved that a particular NP problem has the property that if it is solvable in polynomial time, so are all NP problems. This is called NP complete problem. So again, one definition, or again some alternative definition is they have proposed. They propose the definition for the NP complete problem. Meaning is that NP problem they has the property that if it is solvable in polynomial time, so are all are NP problems. So if they are solved, they can be solved by polynomial time. So all they are called as a NP problem. So that is called as a NP complete problem. One more definition. So let us see here, if L1 and L2 are two problems, for example, then problem L1 reduces to L2. Suppose L1 reduces to L2. If and only if there is a way to solve L1 deterministically polynomial time algorithm that solves L2 in polynomial time algorithm. What is the condition? Where L1 is to be solved by deterministically polynomial time algorithm, and that solves the L2 in polynomial time algorithm, that solves L2 in polynomial time. So meaning is that L1 reduces to L2, denoted as L1 alpha L2, that is nothing but L1 reduces to L2. And when you say that problem L1 is reduces to L2, when the problem L1 is solved by the deterministic polynomial time algorithm, the same way the L2 is solved by a polynomial time algorithm, right? So there exists a polynomial time algorithm which solves L2, then we can solve L1 in polynomial time. Means converse also true in polynomial time. That is, L1 reduces to L2, L2 reduces to L3, hence L1 reduces to L3. Getting this point? So we are reducing L1 to L2, L2 to L3. So definitely, ultimately we write L1 problem reduces to problem L3. So a NP problem such that if it is in P, then NP equal to P. If a problem has this same property, then it is called NP hard problem. Thus, the class of NP complete problem is the intersection of NP and NP hard classes. So means we are here defining or discussing the NP hard problem, or which problems are called as a NP hard problem. So see here, from the figure, it will becomes more clear to you. P problems, your NP problem. So NP problem, we can say NP problems, and the P is nothing but the subset of your NP problem, right? There is another class that is called as the NP hard problems, right? And the intersection of your NP and NP hard, this is nothing but your NP complete problem. This is nothing but your NP complete problem. So NP complete problem means when, yes, no doubt, they are the decision where you are, these are the decision problem, as well as this NP hard, when you are called as a hard problem, NP hard problem, these are the optimization problem. They are the optimization problem. So TSP, if you go with optimization, it falls under the category of your NP hard problem. But the same TSP, traveling salesperson problem, if you go for the decision making, so it falls under the category of NP complete problem. Get this point? So this is the way, or how they are related. So NP is the major class. All the non-polynomial time algorithm, or the non-deterministic polynomial time algorithm, it is nothing but your NP. So majority of problems, they are falls under this category. And the P, that is nothing but the polynomial time algorithm, or the P class problem, they are nothing but the subset of NP. They are nothing but the subset of NP, non-deterministic polynomial time algorithm. So relationship between P, NP, and NP complete and NP hard problem is shown with this diagram. Normally, decision problems are NP complete problems and optimization problems are NP hard problems. However, if problem L1 is a decision problem and L2 is optimization problem, then it is possible that L1 reduces to L2. If it is a decision problem and L2 is a optimization problem, then reduction of L1 to L2 is possible. Example, Knapsack decision problem can be reduced to a Knapsack optimization problem. It can be reduced to Knapsack optimization problem, right? So there are some NP hard problems that are not NP complete. So yes, of course. So there are some NP hard problems. Suppose these are the instances of NP hard problem, but they are not the NP. They are not NP complete problems, right? So not all NP hard problems are NP complete problems. So there are some different sets. There are certain sets. The or limited number of problems they falls under the category, though they are NP hard, but they falls under the category of NP complete problem. For example, is halting problem. So halting problems falls under the purely NP hard problem, halting problem of the Turing machine of or halting problem. So we can call it as a NP hard problem. It's purely NP hard problem. It is not under the category of NP complete problem. Getting this point? So that is nothing but your relationship between your NP class, the P class, NP complete, and NP hard type of the problems. Okay. So in this session, we discuss about the non-deterministic algorithm. So non-deterministic algorithm basically means your deterministic one. So in that deterministic one, I can have the fixed path available. So fixed steps, fixed path, you can call it as a fixed steps are available, or fixed procedure is there, so that I can able to reach to accept either yes, accept, or reject, yes or no. The fixed solution I can reach. But I mean that is nothing but your deterministic. That is nothing but your deterministic problem, right? In case of non-deterministic, you cannot determine where to go, where is the actual path, how to solve that particular problem. So these multiple number of paths are there. So multiple number of paths you can find here. So from which path we have to follow, where to go from which this current location. Suppose you are at this location, from to which path I have to go, so that I can reach to a proper, I can reach to answer either accept or reject, or yes or no. So maximum time the reject, or no is there. So somewhere you will get here yes. So somewhere you will get here. So that is nothing but your trial error method. This method is nothing but your trial error method. So based upon this non-deterministic approach, this is nothing but the approach. So why this explanation is there? The approaches of the algorithm are in this way. If the deterministic polynomial time or the P-type problem, they follow the approach. They have the fixed method, they have the fixed algorithm, the fixed steps are being followed, and they either wish to accept or they either wish to reject state, or yes or no state. But in case of non-deterministic algorithm, non-deterministic in the sense, yes, no fixed pattern is there, no fixed criteria is there. You have to go through the trial and error, right? So in case of polynomial time, so you have the P class and you have the NP class, polynomial time and the non-polynomial time. So non-polynomial time, more correctly it is called as the non-deterministically polynomial time, non-deterministic polynomial time. Getting this point? So solution is available to this non-deterministic type polynomial time. So NP, so this NP, it is further categorized into NP complete and NP hard, right? So NP complete and NP hard. So NP complete means what? Which problem? So the problems, NP problems which are reducible, they are reducible if the polynomial reduction is possible. If the polynomial reduction is possible, then we can say that they are the NP complete problems. And NP hard problems, the problems we can say that the basically if it is a decision problem or it is optimization problem. So optimization problems are always your NP hard problem, or they are always called as a NP hard problem. We're getting this point. So in this session, we discuss about the non-deterministic algorithm, NP complete problem, and NP hard problem. So just go through it once again, just revise this concept so that it will become more clear to you, right? So course outcome attainment to express the understanding of the computational complexity. The standard reference book, always go for the standard books. So let us stop here for the today's session, right?